Imagine a structure so tall it seems to pierce the very heavens. This is not the realm of fantasy, but the reality of skyscrapers. These towering marvels of human ingenuity are not just architectural wonders, but symbols of our progress, ambition, and resilience. Skyscrapers are more than buildings. They are testaments to the indomitable spirit of mankind, stretching towards the sky, refusing to be confined by the limits of the ground. Skyscrapers have a rich and fascinating history, dating back to the late 19th century. The birth of the first skyscraper, a mere 10-story structure in Chicago, marked a turning point in architectural design. From then on, the sky was no longer the limit. Over the decades, these structures have evolved, growing taller and more intricate, with designs that defy convention and inspire awe. Today, skyscrapers are integral parts of modern cities, dotting the skyline with their towering presence. They serve multiple purposes as commercial hubs, residential spaces, or simply iconic landmarks. They are spaces where people live, work, and play, encapsulating the hustle and bustle of city life within their steel and concrete frameworks. But beyond their aesthetic appeal and functional utility, skyscrapers represent something more profound. They are physical manifestations of our relentless pursuit of knowledge, our innate curiosity, and our relentless drive to push boundaries and redefine what's possible. Think about it. These structures tower hundreds, sometimes thousands of feet into the sky, standing firm against the elements, resisting the forces of wind and gravity. They withstand earthquakes, storms, and the passage of time, remaining steadfast in their stature. This is no easy feat. It requires a deep understanding of physics and engineering principles, a meticulous attention to detail, and a daring spirit that dares to dream big and defy the odds. But how do these colossal structures stand tall against the forces of nature? The answer lies in the marvels of physics and engineering. So, buckle up as we delve into the fascinating world of skyscrapers, exploring the science and engineering that make these architectural wonders possible. Prepare to be amazed, because what you're about to discover is truly mind-boggling. At the heart of every skyscraper, there is a skeleton, a steel or concrete frame that bears the weight. Just like how our bones support and give shape to our bodies, the structural frame of a skyscraper does the same job for these towering giants. It's the unsung hero, the backbone that holds everything together, standing tall against gravity's relentless pull. This skeleton, though hidden behind a shiny exterior, is a marvel of engineering. Its primary function is to support the load of the building. Now, you might be wondering, what exactly do we mean by load? In the world of architecture and engineering, load refers to the weight that a structure must support. For a skyscraper, this includes the weight of the building itself, the people and things inside it, and the forces exerted by the wind and even earthquakes. There are two main types of loads that these structures must bear. The first, dead load, is the weight of the building itself. The walls, floors, and yes, even the skeleton. This is a constant, unchanging weight that the structure must support at all times. The second type, live load, is the weight of the people, furniture, and everything else that may come and go. This load can change and move, which adds an extra level of complexity to the engineer's task. The structural frame of a skyscraper is designed to distribute these loads in a way that keeps the building stable and safe. It does this by channeling the weight down into the building's foundations, which then spread it out into the ground. This is why skyscrapers don't just topple over. Their weight is effectively spread out and balanced. But it's not just about bearing weight. The skeleton also gives the skyscraper its shape and allows for the creation of large, open spaces within. Without this structural frame, our city's skylines would look very different indeed. This skeleton, invisible to the naked eye, is what enables the skyscraper to reach such dizzying heights. It's the unsung hero, the silent partner, the hidden hand that shapes our cities and touches the sky. Skyscrapers don't just have to support their own weight, they must also withstand the forces of wind and earthquakes. Imagine you're standing in a field on a windy day. You can feel the gusts pushing against you, but it's not too difficult to stay upright. Now picture yourself as a skyscraper, 100 times taller and thousands of times heavier. The wind doesn't just push, it hammers, it buffets, it relentlessly assails you. And yet you must remain unyielding, a sentinel against the storm. How does this happen? It all starts with the shape. Engineers design skyscrapers with aerodynamics in mind. Just like an airplane wing or a car body, the shape of the building can help to reduce wind resistance. Some skyscrapers taper as they rise, while others twist or feature setbacks. These designs serve a dual purpose. They are not only aesthetically pleasing, but also help to divert the wind, reducing the force it exerts on the structure. But designing for wind isn't just about the shape. It's also about testing, and that's where wind tunnel experiments come into play. Just like how car manufacturers test vehicle designs in wind tunnels, architects use scaled-down models of their skyscrapers to understand how wind will interact with their buildings. These tests help to predict and mitigate the effects of wind, ensuring the safety and comfort of the building's inhabitants. But wind isn't the only force skyscrapers have to contend with. In areas prone to earthquakes, the ground beneath a skyscraper can become an enemy. To ensure the building can survive such a catastrophic event, engineers employ a variety of strategies. Some use base isolation systems, where the building rests on flexible pads that absorb seismic energy. Others use dampers, devices that absorb vibrational energy, reducing the sway of the building. Despite the monumental challenges, skyscrapers continue to rise, a testament to human ingenuity and our desire to reach for the skies. Through design and engineering, these towering structures are able to withstand the forces of nature, standing as beacons of resilience in our cities. Through ingenious design, these towers of glass and steel stand firm against the might of nature. Scene script: without elevators, skyscrapers as we know them would not exist. Imagine living or working on the 100th floor of a building and having to use the stairs every day. It sounds exhausting, doesn't it? This is where elevators come into play, making the concept of skyscrapers feasible and practical. They are the unsung heroes, the vertical transportation system that brings the enormity of skyscrapers to a human scale. Designing and installing elevators in skyscrapers is not as straightforward as it might seem. Engineers face a myriad of challenges. For one, there's the issue of space. Traditional elevators, with their vertical shafts and bulky machinery, take up a significant portion of a building's footprint. To mitigate this, engineers have developed innovative solutions like twin elevators, where two cabins operate independently in one shaft, effectively doubling the capacity without increasing the space required. Another challenge is the speed. How do you move people quickly to avoid long waits, but also safely and without causing discomfort from the rapid change in altitude? The answer lies in the careful balance of speed and acceleration, coupled with pressurized cabins to prevent ear popping, much like an airplane. Safety, of course, is paramount. Elevators are equipped with multiple safety systems, including electromagnetic brakes and backup power supplies. In the event of a power outage or mechanical failure, these systems ensure the elevator comes to a gentle stop. And then there's the question of efficiency. How do you ensure that the elevators are not constantly stopping at every floor, slowing down the journey for everyone inside? Engineers have solved this with smart systems that group passengers by destination floor, optimizing the number of stops and reducing travel time. The world of elevators is one of constant innovation, striving to make the journey up and down these towering structures as seamless as possible. Whether it's introducing energy-efficient designs or developing elevators that can move sideways as well as up and down, the quest for perfection never stops. The humble elevator, often overlooked, is truly the lifeline of every skyscraper. The skin of a skyscraper, its facade, is more than just a pretty face. It's a common misconception that the facade of a skyscraper is merely an aesthetic feature, but it's much more than that. It's an integral part of the building's anatomy, serving functions that are crucial to the skyscraper's existence. Imagine the facade as the skin of the building, controlling the amount of heat and light that penetrate into the interior. This is not just about comfort, but also about energy efficiency. By managing the heat gain and loss, the facade can significantly reduce the energy demands of the building's heating and cooling systems. In a world where sustainability is no longer a luxury but a necessity, this function of the facade is of paramount importance. In addition to heat and light control, the facade also contributes to the overall structural strength of the skyscraper. By bearing some of the wind load, it helps to reduce the strain on the building's core and frame. This is especially important in tall buildings where wind forces can be incredibly strong. So, how has the facade evolved over time? Well, advances in materials and technologies have revolutionized skyscraper design. Modern facades are not just glass and steel, but a complex assembly of various materials, each with its own properties and purposes. Innovations like double-skin facades, smart glass, and photovoltaic panels are pushing the boundaries of what's possible, transforming skyscrapers into self-sustaining, energy-efficient structures. And it's not just about functionality. The facade is also an opportunity for architects to express their creativity, to make a statement. Each facade is a work of art, reflecting the vision of its creators and the spirit of its time. It's what sets one skyscraper apart from another, giving each its unique identity. So next time you look at a skyscraper, remember to appreciate its facade. It's not just a pretty face, but a marvel of engineering and design. The facade, a perfect blend of form and function, is what gives each skyscraper its unique identity. As we look to the future, the skyline of our cities will continue to evolve. Imagine an era where skyscrapers are not just towering structures of steel and glass, but living, breathing entities. As we advance, our architectural designs are becoming increasingly innovative, focusing on sustainability and mixed-use developments. The skyscrapers of tomorrow will be green buildings, incorporating elements of nature into their fabric, blurring the lines between the urban and the natural. This trend of green buildings is not just about aesthetics. It's about creating sustainable ecosystems that contribute positively to the environment. Imagine skyscrapers covered in greenery that absorb carbon dioxide, cool the surroundings, and create habitats for birds and insects. They will harness solar and wind energy and recycle water, reducing their carbon footprint and contributing to a more sustainable future. Mixed-use developments are another rising trend in skyscraper design. It's about combining residential, commercial, and public spaces into a single building. This not only maximizes the use of space, but also creates vibrant, self-contained communities where people can live, work, and play without having to travel far. It's a concept that can revolutionize urban living and reduce our dependence on cars, thereby reducing pollution. Now, let's talk about some of the proposed projects that could redefine our concept of a skyscraper. There's the Shimizu Megacity Pyramid in Tokyo, a pyramid-shaped building that could house up to 1 million people. Then there's the Sky Mile Tower, also in Tokyo, which aims to be twice as tall as the current tallest building, the Burj Khalifa. there's also the concept of underwater skyscrapers like the Ocean Spiral, a proposed underwater city that could accommodate 5,000 residents. And then there's the idea of vertical farms, skyscrapers filled with crops that could provide food for entire cities. The skyscrapers of the future will not just be taller, but smarter and more sustainable. They will be more than just buildings. They will be habitats, ecosystems, communities. They will be a testament to our progress and our commitment to a better, more sustainable future. Skyscrapers, these titans of steel and glass, are a testament to human ingenuity. As we reach the final stretch of our exploration into the physics and engineering of skyscrapers, it's time to revisit the key points we've navigated so far. Our journey began with sowing the seed of intrigue, where we unmasked the mystique of these towering structures. It's not just about their awe-inspiring heights, but the intricate ballet of science and design that makes them possible. We then delved into the backbone of skyscrapers, the structural system that bears the weight and keeps these giants standing tall. We learned that the heart of the matter lies in the core, the rigid inner structure, and the external frame that works in unison to distribute weight and withstand the pull of gravity. But these structures aren't just battling gravity, they're also up against the forces of nature. We discussed how engineers design these buildings to resist wind forces, earthquakes, and even the effects of sunlight. By incorporating clever design elements like tapered shapes, aerodynamic features, and seismic isolators, these lofty marvels are built to sway, not to fall. Next, we turned our attention to the lifeline of skyscrapers, the intricate network of systems that make these buildings habitable. This includes everything from the plumbing and electrical systems to the elevators that shuttle people up and down. It's a complex web of services, all working seamlessly behind the scenes to keep the building alive and functional. The skin of the skyscraper, its facade, was our next focus. This isn't just about aesthetics. It plays a crucial role in maintaining the building's internal environment and energy efficiency. We learned how modern facades are designed to balance natural light with thermal comfort, all while presenting a pleasing exterior to the world. The future of skyscrapers was our penultimate stop. We explored how emerging technologies and sustainable practices are shaping the skyscrapers of tomorrow. With innovations like vertical forests, energy-generating facades, and 3D printed components, the future is set to be even more exciting than the present. The physics and engineering of skyscrapers is indeed a fascinating and complex subject. It's a testament to our ability to overcome challenges and push the boundaries of what's possible. It's about more than just building tall. It's about creating sustainable, livable spaces that enrich our cities and our lives. As we marvel at these soaring structures, we are reminded of what we can achieve when we reach for the skies.